Hello, so this is a video for COMP345. This is for week 5. This is talking about arrays. This is the second part, the second video for this slide set. Here we're going to talk about dynamically allocated arrays and various other solutions, like in standard arrays and a little bit about boost arrays and STL containers. So let's go to the slides. Okay. So the first video we were talking about the statically allocated arrays. That's basically arrays that for which you define the size at compile time, and the size is to remain the same for the entire duration of the execution of the program or the scope in which this variable is existing. For dynamically allocated arrays, it's not a magical solution. It allows you to somehow make change in the size, but it's not as easy as one might hope. If you want to have something that is more dynamical or dynamic, you have to use STL containers. Even if you use STD arrays or boost arrays, they are still arrays that are statically, whose size is statically determined at compile time. The only way to have something entirely dynamic, which the size can change any time you want very easily, you have to use containers. So there are, as we saw earlier, there are a lot of limitations in using static arrays. So why do they exist, you might say? Well, because they are extremely efficient. Okay, so if you are to store a series of values and you know how many values you have to store, it's always the same number of values you store, and you need efficiency, then you should use a statically allocated array. That's for sure. That's the most efficient way to store an array. The downside of it is that it's constant. Its size is absolutely constant. It's very efficient, but it's not flexible at all. Especially if you want to pass arrays to functions, you can, but it's not very flexible. Okay. Again, if you want flexibility, you probably want to use containers. If you want efficiency, you probably have to deal with the lack of flexibility of an array. So you may use what's called partially filled arrays. There is some examples in the lab, the lab code. You may want to look upon that. So that a partially filled array is basically an array that you define of kind of the maximum size you think you will need. And then you basically leave some of the elements empty. Okay. So of course that needs to be managed as to what part of the array is really used. So you need to have some kind of marker as to what's the used size of the array. So yes, there are solutions like this, but it's not very efficient because then what if you're defining an array of 100 and you use only 10 slots in the array? And of course, you are consuming much more memory than you would that you need most of the time. So that's wasteful memory. More flexible, but wasteful. There's always this compromise that you have between efficiency and consuming more memory and potentially even running slower. As I will hint at later on when we talk about STL containers, they seem to be a magical solution, but there's a cost in using them. They consume more memory and they are somehow slower than to access and to use than arrays. So if you use dynamic arrays or dynamically allocated arrays, so you can somehow change the size of your array. Okay, as we will see, it's not as flexible as you may hope. So what's happening is your dynamic array is essentially, or dynamically allocated array is essentially a pointer to a static array. so that you can actually have this pointer to point in time. Let's say let's say that the size that of the array that it points to now is 4, an array of 4 integers. Let's say you want to increase it to 10. Then what you would do is you create a new array of size 10, and then make this pointer point to this array of size 10. So this array that you have declared, the name that you use is actually refers sometimes in the first place referred to an array of 4, and now it refers to an array of 10. So you have somehow changed the size that this variable, this pointer variable is, size of the array that this pointer variable is pointing to. So apparently you have changed the size of the array, but literally you have made this pointer point to a different array of a different size. So there's, of course, management. If you want to increase the size of the array, you have to not only create the new array of the bigger size, for example, you also have to manually copy the values into the new array. Okay. So yes, it's not magical. It's far from being magical and very easy to use. Again, if you want things that are easy to use and manage for you, you use STL containers. So how do you create this dynamically allocated array? So let's say you want to create an array of 10 doubles, then you basically create a pointer to a double. Remember when we talked about in static arrays, we talked about the fact that your array name can decay into a pointer. So here you're kind of like using this concept here by saying, okay, I'm going to create a pointer to a double named D, and then I'm going to assign this array of 10 double to my variable D. So you essentially here decaying this array of 10 doubles into an address, and then you're putting this address into this variable D. Okay. But here, the difference is that you are actually manipulating literally a pointer to a double, whereas in the static array case, there's no such thing as this pointer, literally the pointer in your code. If you would have an array D of a 10 double, which is a static array, you could not refer to D as a pointer unless you actually decay this pointer to a double. In this case, if you manipulate D, it's literally an array, it's literally a pointer to a double. Okay, so note that, well, you might say, well, that's one and the same because here there's a constant. Well, the thing is that when you use the new operator on an array, this here does not need to be a constant. So it could actually be a variable that you have here, okay, allowing you to create an array of different size depending on certain situations, okay? So no, this does not need to be a literal here when you use the new operator to create an array. So of course, then what happens here, and that's what I drew on the board here, if we can see more here. So here I'm creating this array, this pointer to an int named a, and then I say a is equal to new int of 4. So this is creating on the stack, on the heap, a new array of 4. So that's creating this new array of 4 here on my heap. And then this returns a pointer, which I then assign to my variable a. Okay. So then a is now pointing to this array of 4 integers. So note that here what's happening is that now the only thing that is on my stack frame is this pointer here. The array itself is actually residing on the heap. That's one notable difference between using static arrays and dynamic arrays. If you use static arrays, then the entire array would reside on the stack. Whereas if you use a dynamically allocated array, the array resides on the heap. Another consequence of that is that now you have pointers to some things that have been allocated. So you use new here. So if you don't use delete somewhere to actually free this memory here, the A is going to result in a memory leak. For example, if you declare this variable A here in a certain function, and then you create this array in the this pointer to an array, or you make this pointer point to this new array here, and then you basically return from this function before you can actually do delete, then this will be lost. So this would be a memory leak. Okay, so this would be freed automatically by the runtime system because it resides on the stack. But this here would not be freed unless you can actually unless you actually call delete before you go out of scope. Okay. Well, another thing also is that it would not be a memory leak if, for example, this would be in a function, and then this function would actually return A, in which case the function would return this pointer to the calling function, and then the calling function would still have a pointer to it with which it could call delete on this here. Okay. So I repeat this concept of a memory leak. Memory leak is happening when you have a pointer to something that resides on the heap, and at some point in time you lose the last pointer that you have that is pointing to this thing that you have reserved on the heap. Okay. So repeat, if this isn't a function and it does not return the pointer, then if you get out of this function before you actually delete that, then this would be a memory leak because you would have the pointer to this is local to this function. There's only one pointer to this here. So you basically lost the only pointer to this, so that becomes a memory leak. If this function that contains this code here would actually return this pointer to the calling function, then the calling function now has still a pointer to this. So now this is not a memory leak at this point. Okay. But once you will lose the last pointer that you have on something that you have allocated, then that becomes a memory leak. Okay, so let's return to slides. Okay. So how does this work if I want to create a, or if I want, yeah, okay, let's go to deallocate. We'll go to multidimensional after. So if I want to deallocate, to delete this array, or to deallocate the array that have that array that is pointed to by my pointer, and what I have to do is to call delete. You know, when we created a pointer to an object before, as we saw, then you call delete and then the name of this pointer. Now there's a special syntax if you want to call delete of an array, of a static array that you have allocated on the heap. You have to use the angle brackets here. Okay, so you go delete, open, close angle bracket, and then the name of this pointer that points to your array. So that's going to take care of deleting the entire array here. Okay. So as for any other pointer, after you call delete on this thing here, after in the slide, if you call delete on D, then the memory has been deallocated, but D still contains the address of this here. Okay. So in the immediacy of this operation, right after this operation, this is pointing still to this array that is still there. But as soon as you will call new, you run the chance that this memory space here is going to then be allocated to another variable. At which point, if you still access these values here, this will be the values that are used by another variable. And of course, that does not going to result in something that makes a lot of sense. Okay. So that basically, once you call delete on a pointer, it becomes a dangling pointer. Dangling pointer is a pointer that points to a memory space that was allocated properly, and then you delete and free this memory space. So basically a dangling pointer is pointing to a freed memory space. Potentially that will eventually be pointing to something that later on is going to be allocated to another variable. That's why dangling pointers are problematic. You can still dereference them and access the values, but of course that's later on, it's not going to be values that still belong to this object that you had allocated there. So very good practice is always when you call delete, you set this variable to null to make it so that you cannot anymore dereference this pointer, because you can't dereference a null pointer. Okay, so then question becomes, how does it know what is the size of this thing here? The fact of the matter is that when you call new and you create an array, when you use new to create an array, it somehow stores the size of the array inside of the memory that is allocated here, so that it can know when you call delete what is the size that it needs to deallocate. Okay, now that's not something you can access programmatically speaking, but it stores the size inside of an additional memory cell, basically contains the size. And then the runtime system knows when you call delete, it knows where to find this size to know what size of memory to actually free. So that's in the semantics of the square brackets operation using conjunction, with delete. Okay, so how does it work when you have multi-dimensional arrays? So now it looked quite simple here, but we'll see that it's a little bit more complex than dynamic arrays, but multi-dimensional dynamically allocated arrays are even more complicated. Okay. Well, once you know how they work, fine, but it's a little bit of gymnastics. Okay, so you can create multi-dimensional, any number of dimension for a dynamically allocated array. The thing here is that you're going to use for each additional dimension, you're going to use an additional layer of indirection between the original pointer and the actual rows that are stored in the multi-dimensional array. Okay, so I'm going to explain this here. Let's go here. So here I have this, see this here. Let's make this like this. So here I have, I want to create an array of 3 by 4. Okay, so what is an array of 3 by 4? If you remember in the last video, when I talked about static arrays, basically when you have an array of 3 by 4, it is essentially an array of 3 rows of 4. Okay, so it's the same concept here. So basically you have this array that's named it A, which is an array of a row of 3 pointers to integers. And then each of these pointers will point to 1 row each. Okay. So that makes actually this pointer here a pointer to a pointer. Because if you see this graphically here, what's happening is that you're creating a pointer here that is the variable that you're declaring to be used as your multidimensional array. It is, much like here, it was a pointer to this array that you use in the heap, that you allocate in the heap, except that here you need this additional level of indirection. So you make actually this pointer A point to an array of each a pointer to these rows of 4. Okay, so that's why these are each pointer to an int. So in fact, this needs to be a pointer to a pointer to an int. Okay, if you would have a 3-dimension, then the A would need to be a pointer to a pointer to a pointer to an int that points to as many, basically you would have another layer of interaction of pointer. Okay, so you would have a pointer to a pointer to pointer to an int that points to an array of pointer to an int, which themselves point to a lot of different arrays of pointer to an int, which themselves point to your arrays of int. Okay, you add another dimension, you add another indirection level using another layer somehow of pointers. Okay. So this was a one-dimensional array of int, dynamically allocated one-dimensional array of int. So it's a single pointer to an int. Two-dimensional, you need to have two two indirection levels. So that's pointer to an int. So that's 2 dimensions. If you want to have 3 dimensions, then you would have 3 stars. Okay, so one thing that's very important to realize here is that I try to make it simple here, but it's deceptive to think, you would be wrong to think that these arrays here are stored contiguously. Remember when we saw the static arrays, one of the very convenient things was that the array, all the rows of the array were all stored contiguously in the computer's memory. Okay, and then that's why it could be very efficient using pointer incrementation to access all the elements. However, here what's happening is that when you create each of the rows, you call new, like new to create a row, new to create a row, new to create a row. So the runtime system is going to basically be asking the operating system, give me a block somewhere on the memory that you have signed to me. So basically the operating system is going to find the first block available and then give it to it. So these are essentially going to end up being scattered all over the place in the memory allocated to the process that runs this program. Okay, so you cannot anymore assume that, for example, this is contiguous to this. Okay, so this is somewhere, this is somewhere else, this is somewhere else. Even this is somewhere else. Okay. So all of these parts are scattered all over the place, so you cannot loop over sequentially all of them. So that's one of the disadvantages of this way of doing. So it's more flexible, but it loses this convenience of being able to increment a pointer efficiently to actually loop over all the elements. Okay, that's it for that. Okay, so that's basically what I had on the board here. You have your pointer to an int, which points to an array of pointers to ints, which points to an array to each an array of ints. Okay. Again, important here is that only your original pointer to an int resides on the stack. Even this one here, even though it's an array of pointers, you might say, oh, it's an array of pointers, it belongs to the stack. No, because here you've used new to create this array of pointers to int. So even this array of pointers to int is residing on the heap. Okay. Only the single pointer here is pointing to all of these things here, or it's pointing to the array, the first indirection array. So only this one resides on the stack. Then if you want to delete, then you have to actually delete it in exactly the same order, but in reverse order. So the first thing you did is to actually call new to create your array of pointers. First thing you did, you call new to create your array of pointers. Then you call new on to create each of the rows of your array. Now, if you want to delete this whole thing, first thing you have to do is to delete every row. So basically you're going to call delete on each of these here. Then when each of these have been deleted and freed all the rows, then you will actually call delete on that. Okay. If you call delete on that first, then it's going to free this here, and then all of this here is going to become a memory leak. Okay, that's why you have to delete them in reverse order. Okay, if you would have, again, multiple dimensions, you would still have to go exactly in reverse order, deleting all the rows and then deleting the latest layer of indirection of pointers, and then so on, going up to eventually deleting the first pointer. Okay. Of course, normally you would do a for loop or embedded for loop if you have multiple dimensions to do this creation or memory allocation, calling new on the to create the array. You'd use embedded for loop, and then to call delete, you create an embedded for loop that goes in reverse order. So you see that every time you need to create your dynamically allocated array, you need to call new on each of these things here and have an embedded for loop, and so on and so forth. And every time you want to delete, then you have to have an embedded for loop. And then it's not as, easy as you might wish. Okay. It works, but it's not that easy to use. Okay, that's why you would kind of seldom see code, C++ code that would use multidimensional dynamically allocated arrays. Okay, other solutions. So we saw static arrays, extremely efficient, but very inflexible. And we saw dynamically allocated arrays, a lot more flexible, but very cumbersome to manage. Okay. So then what are other intermediate solutions or more flexible solutions? Because neither of these two first solutions I've shown are very flexible, right? Kind of hard to manage. So you can use the array class that is defined in standard C++. So that's std : array. So it's essentially, it is a class that allows you to store an array. It has some member functions that allow you, for example, to get the size of the array and things like this. So it provides you with interesting features. Okay. But it is still a statically allocated array. Okay. It provides you some features that make it more usable, but it's still a fixed size. There's also Boost library that has array. There's also plenty of other libraries that you will come across that define their own array class. Some of them are more flexible than others. They all have their own particularities. But the thing is that if they are to be very efficient, then they will be somehow inflexible. Okay. If something is flexible, it means that it's probably less efficient than something that is not flexible. There's a compromise between these two. So yeah, so here this is examples using std array. So you see here, I'm using string, I'm using iterator, I'm using algorithm, and I'm using array. So these are all things like IO streams defined in the standard library. These are all other libraries that for example, I never used yet algorithm or array. There's plenty of things in standard C++ libraries. Okay, so here this is an example of how to use the algorithms that pertain to the arrays. So here this is how you declare an std array. That's basically an array of 3 ints named A1, and here you provide the values to initialize your array of 3 ints. There's some variation, as I hint at here. When you use this squiggly brackets notation, depending on which standard you use, you may or may not have to use double brackets. Okay, if you have a multidimensional array, then you would have to use embedded brackets. Okay, the latest versions of C++ allow you to use only one list, even that without embedded brackets, even if it's multidimensional. Okay. Other things here, you can assign arrays. So the assignment operator is defined, copy constructor is defined for this array class, and so on. So these are all things that are done for you. Okay, if you want to copy arrays, it's a class. It implements the necessary machinery for you to manipulate them. Another thing is that there are some algorithms that are defined in the standard library for algorithms. The algorithm as file in the standard library, essentially. So you have, for example, sort. So when you call sort, you can actually refer to the certain elements inside of the array that you have defined here. So essentially here you want to sort the elements from the beginning of this array to the end of this array. So essentially these are two iterators. Okay, I'll come to that a little bit later. An iterator is basically some kind of pointer that you have to point to different elements in the array. It's, as the name says it, normally it's used to iterate over all the elements using some kind of pointer. You have some pointers that are predefined, such as begin and end for the containers for which it makes sense, such as an array. So basically here you tell the sort algorithm that is in this file here to sort the elements of A1 from beginning to end. Okay. Then you use another one here. I'm not going to go here. There's going to be a lot of examples. I'm not going to go into all the details. I'm going to assume that this is done by the lab instructors. Okay. There are plenty of examples in the lab material about the SDL containers and the algorithms and so on. I'm going to go quickly over them here, but if you want more details, go to the labs. Okay, another thing that is enabled, and that's the kind of thing that I'm not covering that much in this course, but there are some more advanced features, not that they are like things that are very new, but are more advanced features. Like, for example, you could have what is called a ranged loop. So you have a for here. So essentially, you loop over A3. You loop over the elements of A3 using a variable S. Okay. So essentially, that it's inherently using some kind of iterator over A3. Whereas your variable that you use to loop over all the elements is actually named S. Okay, so that's what is a range loop. Here you have the thing, after the colon, you have the thing that you loop over, and here you have a declaration of the variable that you use to actually loop over all the elements. And this variable is going to successively take the value of each of the elements as you encounter them in this container here. So then you use that to actually output all the elements from the array A3. Now, why is its name auto? Auto is another of these advanced features that allows you to declare a variable of an automatic size. So in this case, the size can be determined because the type of A3 is an array of string. So then the compiler figures out that if S is used as an iterator on A3, which is an array of string, then it figures out that S at runtime is going to be a string. Okay. So in cases where you may want to use a variable that is going to take different types in time, when it is possible to be determined at compile time, then you can use auto. Okay. Okay, what else? Okay, let's go to, so this is for STD array. Okay, this is still not SDL containers. So here we go on SDL containers. Remind you that the STD array is a statically allocated array. Its size will not change. You cannot change its size. It provides you with convenient aspects of it. Like, for example, you can have iterators over it. You can use these algorithms with it and so on. It's very convenient, but still it's fixed size. Okay, and what about the STL containers? So many people that know how to use C++ will use containers all the time. Okay, such as a vector is probably the most prevalently used STL container. There are a very large amount of containers of different characteristics, I might say. For example, you can have a queue, you can have a list, you can have a doubly linked list, you can have bags, there's all kinds of containers. Okay. So depending on what situation you are in, then you would use a different kind of container. So conveniently, you have a lot of students are taking COMP352 data structures at the same time as this course. The SDL containers are very good to actually teach how to program using these data structures that you learn into in COMP352. Okay, so the SDL containers, it actually define, the name says it, containers that can contain values of the same type, such as an array that we saw before, but you can have different kinds of containers. For example, an array is a ordered container. Okay, that's why you can refer to element number 0, 1, 2, 3. For example, if you would have a bag, then there's no such thing as order. Okay, so there's ordered containers, there's unordered containers, and so on. Okay, but they are all, a container is all the concept that you have a group of values that are all of the same type. Okay, so particularity of STL containers is that they're much less error prone than basic C++ arrays. Like you have possibility, for example, of doing the boundary checking so that you don't try to access your container outside of the boundaries of the container, such as the problem we had with the static arrays. Okay. Of course, then that comes with a cost. So if the container itself is preventing you from going out of the boundaries, it means that it maintains, it knows what's its own size, and that it makes a check. Every time you want to access something, it makes a check before it gives you the value to see if it is actually out of bounds. And if every time you want to access a value from your container, you make this check and you do this all the time, then of course this makes your container less efficient than the static array, which makes no check. Okay, so yes, very convenient, but also I'm not saying that it's extremely inefficient, but it is more inefficient. It is less efficient than a standard than a static array. It also consumes a little bit more memory because it uses pointers to manage each of these elements that are being stored. It contains, a container contains values such as the size of the container. If it wants to grow and shrink in size, it means it inevitably that it consumes often more memory than the actual number of elements that are stored in the container. Okay, I'll come to that later. Essentially, it's less efficient than the very, very lean and efficient static arrays. If you want to do something extremely efficient, you would use a static array and deal with the inflexibility of it. Okay. So this is here a screenshot. I'm not going to delve into all of this here. This is just to give you an idea that there's a lot of things out there. We're not going to go over all of these things. So some of these things you would see in COMP352 to explain what are the different concepts of different data structures. For example, you have a list, a queue, a stack, a set, a map, a multi-map, unordered set, vector, and so on and so forth. List, doubly linked list. All of these are implemented as STL containers. And they each have their different API, if you might say. So there's different methods that are available to use each of them, depending what kind they are. Okay, for example, if you use an array, then you would be able to use the square bracket notation to refer to elements, for example, element number 1, 2, 3, and so on, because this is an ordered container. However, if using a set, then there's no such thing as the brackets notation because they are not ordered. They don't have a numbers. It's just basically a bag of elements that are not ordered. So there are things that are not available as methods for the unordered containers. So depending on what container you use, it's going to have its own particularities. Okay. So you have to learn how to use each of them when you have to. So that's why we're not going to go into all of them, all of their particularities. Okay, so let's go into, again here, some examples. I'm going to go quite quickly over them. If you want to have some more details about that, go into the examples, run them, the lab examples, listen to the lab videos, go to the lab, ask some questions. Okay. These are actually extracts from the examples that you can find on the lab material. So here I'm creating a vector of int, and then I am inserting in this vector of int values from 1 to 5. Okay, so here you see that I did not have to specify what's the size of the vector when I declared the vector. Okay, just say it's a vector of int. Then I can insert values into it. I can insert as many values as I want. Well, there's an upper limit to the size of any of these things, obviously. But I can actually declare, oh, this is a vector, and then I start adding things to it or deleting things. So it is going to grow, and the memory allocated to it, it is going to grow as I add more things. Okay. I think I described that before. Or did I skip some? Oh no, that's after. Okay, we'll come back to the memory management aspect of it. How does it grow and shrink? Okay. Dynamically. Here, it was originally a vector of int of the minimal size. Then I started adding things to it. If this minimal size is not enough suddenly because I add too many things, then it's going to allocate more memory. Okay, so it goes in cycles like this. I'll come back to that later. Now here I'm using this notion of an iterator. So here this is an iterator that I'm using. So this is a for loop. So the first part of my for loop here is basically declaring what variable I'm going to use as the value to iterate over the elements. In this case, well, when you were using an array, you were using an int to loop over an int that is used as an index. If you're using a container, normally that one of the typical ways to do it is to use an iterator. So you see here that the iterator I'm declaring is of type iterator to a vector of int. So that's essentially the type of this is iterator, but it's an iterator that can only iterate on a vector of int. Okay. Each of the containers have their own iterator types. So here I'm declaring an iterator over a vector of int. Then I say this vector, iterator it is initialized to my vector dot begin. So begin is an iterator that that is returned by this function begin. Okay, so iterator is essentially some kind of pointer that points to a specific element inside of your container. Okay, so my vector dot begin is essentially some kind of pointer to the first element inside of your vector. Now you say this iterator is, you take the value of this pointer, the begin pointer, and you say it is equal to begin. Okay, that's how you start your loop. Then you loop until this iterator is different, or you loop and you stop when this pointer, this iterator, is going to be equal to my vector dot end. So the end is essentially a marker that you have after the last element. Okay, so if you are past the last element, then in this for loop here, you will stop. Okay, so dot end is another iterator that is predefined on the vector. And then here you check if the iterator is equal to the end iterator. And then you increase the value of the iterator. So of course, then that means that the class iterator has overloaded the plus plus operator. So that means this iterator is now, after the plus plus operator is executed, is now pointing to the next value, because vector is an ordered container. Then what I do is essentially I print this value. So you see here that because iterator is a pointer, I have to dereference this pointer in order to print the value in question. Okay, well, that's essentially using an iterator to print my values 1, 2, 3, 4, 5 that I put into my vector here. Okay, I'm not going to go into all these details with all the other examples. Okay, so again, go to the lab if you want to have more details. This other loop here is showing that you can, okay, what if you want to have multidimensional vectors? So what is a two-dimensional vector? It is a vector of vectors. Okay, pretty much like when we had here, if you have a two-dimensional array of int, it is an array of ints. Okay, so same concept. If you want to declare a multidimensional vector, it's a vector of int. Then you can actually create rows inside of your vector and then assign values to each of the vectors inside of the vector. And then you actually push each row inside of the higher dimensional vector. Okay, it looks pretty much the same as what we were doing here. Okay. Much more interesting here is that the operator square brackets operator, or that you used in your arrays to refer to the elements of your arrays, is overloaded on most of the STL containers, or actually the ordered containers. Or the indexed containers. So you can create a vector of vectors, and then you can actually use the double square bracket notation to refer to the elements just as if it would be a two-dimensional array. Okay. So how this works is that in the class vector, this operator here is an operator that you can overload. So this operator has been overloaded on the vector class, enabling you to use this here pretty much as though it was a two-dimensional array. Now it may seem, because you can write this as so here, you may think, well, oh, that means that this is an array. No, it's not an array. It's just that the square bracket operator has been overloaded so that you can use it syntactically as an array. If you would see behind the scenes what's happening when you execute this, you would see that it's much more complicated than your good old offset calculation that I've shown in the previous lecture. But it's very handy, okay, very intuitive to use because this square bracket notation has been overloaded, or square bracket operator has been overloaded. There's plenty of operators that can be overloaded. I'm not going to necessarily going over all of them here. Okay, so what happens if you want to create or destroy an STL container? So essentially what's important to understand is that STL containers are templates. Okay, so we'll see what is templates later. Anytime that you have the angle bracket notation, like you have a type and then you have angle brackets and then a type in between the angle brackets, this is a container. Of course, you may think, well, this is the same concept as a Java generic class. You would be somehow right, but as we will see when we talk about templates, C++ templates and Java generic classes, they appear to be the same thing, but they're not the same thing. They're the same concept, but operationally speaking, it's very different. So every STL container is a template that you can instantiate by passing to it a certain type parameter. We'll cover that much later. So in this template, which is essentially a template, a class template, everything is defined so that it has its memory management, copy constructor, assignment operator, as I just said, square brackets for those for which it makes sense. That's all this machinery that is implemented inside of the template, which actually is quite an amount of code. Okay, if you would look at all the code for a specific container, like vector, you would realize that it's quite complex. That's the point. When you're using a vector, all these lines of code that define the vector, you are actually executing these lines of code as you're using the vector. That's what makes a vector somehow less efficient. It runs slower than if you would be using the very efficient static array. Okay. Also in this template, there are some variables that are used to manage the size and so on, increase and shrink the size, all this mechanics that is very convenient to use, requires some memory consumption, okay, to manage this dynamic aspect of it. So yes, it consumes more memory also. So it's a little bit slower, consumes a little bit more memory. And you have assignment operators, you have iterators that are defined for each of your STL containers, as I explained before in the previous example I showed. What if you want access? As we saw, you can access the square brackets. You can use the square brackets notation to access the containers, provided that they are ordered containers. Okay, doesn't make sense, for example, if you have a bag to refer to an element with an index. Okay, so let's backtrack a little bit. You have the at function. Okay, so for example, you can create a vector of 5 if you go named v. If you go v dot at 3, that returns element number 3. Particularity of the at is that it will do boundary checking. So if it's a vector of 5 and you do v dot at 1000, at is gonna throw an exception saying that you went out of bounds, much like your Java arrays would do. Okay. Of course, that means that .at is a little bit less efficient. Okay, because it makes the boundary checking. If you use the square brackets notation, does not make any check. So it goes faster, but it's more error prone. Plenty of other things, not going to go over all of this. So you have front and back methods to, if it's an ordered container, the first element is called front and the last element is called back. Don't confuse back and the iterator begin and front with the iterator begin and back with the iterator end. Begin and end are iterators. Essentially, they are a pointer to the first and last element, whereas front returns the first element and back returns the last element. Front and back are not iterators. Begin and end are iterators or constant iterators. Okay, so for the capacity, so how does it go and grow and shrink in size as you go? So first, when you create a container, it is of a predefined size. Okay, I don't remember. Actually, you can define what is the predefined size. I don't remember what it is, but it's of a reasonably small size when you create it by default. Okay, its size when you create it is not 0. It contains some kind of an array of objects of a certain reasonable small size, okay, which are empty for now. Okay, then if you put some values in it, then it's going to put values into this container, into this array essentially. And if you reach the capacity of this initial array, then it's going to basically create another array, bigger one. Then it's going to copy all these elements into the bigger array. And then you're going to be able to use a bigger size vector, for example. And as you grow, then it's going to go do this sequentially as you reach the current capacity. Okay, so that's what's the difference between size and capacity. So size is the current number of elements that you have put in the container, whereas capacity is the size that the container now can actually contain before it needs to grow bigger. Okay. There is eventually a maximal size of any container. You can somehow change it, but rarely do you have to do that. Okay, so there is also some modifiers depending on what kind of container you're talking about. You have insert methods, erase methods, push back, push from, push front, pop back, pop front, clear, swap. So these are all methods that are exposed by many of the STL containers to actually insert values either at the front or a certain index, or removing some values using an index, or removing the first element or the last element. Plenty of things are available. Okay. So warnings. So all of this seems very, how can I say, magical. Okay, it seems that this is the solution and that it's going to solve all your problems. You're going to realize when you use the containers that it leads to a lot of apparently esoteric problems. Okay, particularity, as is for many things with C++, if you want to use something and you don't know how it works internally, then you're going to inevitably misuse it. And then it's going to be very confusing as to what's happening or not happening as you thought it would be happening. So you need to understand how it works internally in order to use it properly, or else it will misbehave in a very confusing manner. Okay. One thing is that eventually, as you store things, as you store elements into the containers, eventually, if you remove, for example, elements in the containers, in the container, it's going to want to call your destructor. Okay, so so that's why if you put elements of your own kinds into a container, it must do appropriately its own memory management. If you put elements of your own kinds into a container, and every time you create an element and you delete it, it creates a memory leak, And every time you create an element, put it in the container, and you remove it, you create a new memory leak. Okay. So the container is not going to just magically make your objects memory leak free. Okay. If there's a memory leak issue in your class that you've created, every time you're going to put an element inside of the container, eventually you're going to have a little bit of memory that's going to be leaked for every element you put into the container. So if you want to use your own classes, your own objects, and put your own objects in a container, make very sure that they are free of memory leaks. Okay, another thing which happens often, I'm not going to point here to all the problems. Be careful when you use iterators to delete elements. Okay, just briefly said here, what's happening here is, imagine you have a container. It contains a series of values. Then you use an iterator to point to a specific element. Then if you actually use this iterator as a pointer to delete this element, then suddenly this pointer is pointing at an element that does not exist anymore. Okay, so which of course is going to create a problem because you're pointing to something that you just said to delete itself. Okay, you just told this thing that you're pointing to delete. So it does not, you now have a point, you just basically created a dangling pointer. So be careful when you, especially when you delete things from a container, and if you're using iterators, it can be tricky. So all this to say, STL containers, they appear to be magical and being a solution to all of your headaches and problems. Not so. You have to learn how they work and deal with their intricacies. That's the nature of much of C++, by the way, if you didn't realize it by this time. Very quickly here, other examples. So here I'm using a queue. So I'm putting things in my queue, removing things from the queue at certain indexes, and so on and so forth, using an iterator on my queue here. Here I'm using a vector, putting elements, removing elements. And then here I'm essentially using the square bracket notation to access the elements here. So you remember the previous example, I've shown you how to use an iterator to loop over the elements of a vector. You can still use this good old notation here that you used to use for an array using the square bracket notation. You're allowed to do that because square brackets have been overloaded for you. However, note that I remind you, if you're using the square bracket notation, it's not going to check, do a boundary checking. So that's one of those things. It seems to be something that is simplifying things, but simplicity comes with a cost, which is that it can go out of bounds. Okay, so I'm going to stop here. So that's it for this lecture. Thank you.